right, we're gonna go ahead and get started with the review. I went ahead and did the vocabulary for you. There's also a key posted on Canvas, so you can go ahead and check that out as well. I'll go ahead and run through these really quickly, 1 through 5. What is the term used? Uh-oh. That was weird. All right, let's try again. What is the term used for a positively charged ion? When you do the vocabulary, you'll see that a positively charged ion is called a cation. I remember it because the T looks like a plus sign. Okay, positively charged. What is the term used to describe a negatively charged ion? This is an anion. Okay. How many valence electrons does oxygen have? Oxygen has 6 valence electrons. Describe the electron transfer when an oxygen ion forms. Remember the octet rule, everything wants 8 electrons. And so when an oxygen ion forms, it will gain 2 electrons in order to meet that octet rule. All right, so it says draw the electron dot notation. This is the Lewis dot notation for oxygen's common ion. So after it's gained those 2 electrons, when it's gained those 2 electrons, we have 1, 2, 3, 4, 5, 6. It had 6, it gained 2, so it should have a full valence shell. And when it does, it has a 2- charge. I went ahead and took the liberty of adding some answers here. These ones are self-explanatory. What's the definition of a polyatomic ion? It's a group of atoms that act as one ion, essentially. 3 examples of polyatomic ions. You can use your polyatomic ion sheet. Okay, so this one, common polyatomic ions. It has the front and the back. Choose 3 of those. This is just to kind of familiarize you with that reference sheet. I chose 4 common ones. There's ammonium, and it has the NH4+. Carbonate is CO3 2-. Sulfate, SO4 2-, and phosphate, PO4 3-. Explain why ionic bonds form between metals and nonmetals. Well, metals tend to have valence electrons anywhere between 1 and 4 valence electrons. Meaning that when they ionize, when they try to get to that octet or to the 8, they want to get to 8 valence electrons. So when they try to get there, it's easier for metals to lose electrons than it is for them to gain them. And so metals are going to lose electrons. Okay, so metals lose valence electrons to meet the octet rule. Okay, so metals are going to lose their electrons in order to meet that octet rule. When they do that, they become cations, which are positive ions. Okay. Now, nonmetals, in order to get that octet rule, nonmetals have valence electrons anywhere from 4 to 7 valence electrons. So instead of losing electrons, it's pretty challenging for an atom to find 7 places to put electrons. And so rather than trying to get rid of 7, 6 electrons, it's going to gain just a couple, 1, 2, or 3 electrons in order to get to 8. So nonmetals gain valence electrons to meet the octet rule. They can get these valence electrons from the metals that are getting rid of valence electrons. So they get these from metals. Okay. Then we have anions. So when nonmetals get electrons, electrons are negatively charged. So when they get these extra electrons, they are now negatively charged. So we have oppositely charged ions. So the opposite charged ions attract one another. Okay. All right. For these names, I'm not going to run through and do all of them. I'll remind you of a couple of rules, but then you can use the key to check them. All right, when we're naming ionic compounds, there's two main rules, or two steps. First one, you name the cation. This is the first element, or first ion. Okay, don't forget transition metals. Use Roman numerals as the charge in the name. The second step, name the anion. Don't forget to drop the ending and add "ide" when it is a monatomic ion. Monatomic just means there's one element. Okay. Polyatomic ions keep their name. Okay. All right. So a simple one, NaCl. If we look at the periodic table, Na is our cation. It is sodium, and cation ions keep their names. Okay, they don't change their names. Our next element is Cl, that is chlorine. However, when we name the anions with one type of atom, we have to drop the ending and add IDE, so it's sodium chloride. Okay. Now here, we'll do this one, D, CaOH2. So the first step, name the cation. Ca is one element, it's our metal, so that's our cation. Ca is calcium. Calcium. So now that we've named our cation, the only thing left that we have to name is one ion, our anion. Okay, there's only one ion, but there's two elements here, O and H. Well, an ion with more than one atom is a polyatomic ion. So we have to go to our polyatomic ion sheet in order to name this guy. So we got to go here. All right, if I look it up, I look for OH minus, and I see that this is hydroxide. So the whole thing is hydroxide. So this is calcium hydroxide. Okay. Let's do a couple of these maybe. All right. Now remember, if it's a transition metal, this part right here is what we're looking at. If it's transition metal, when we're naming it, we have to use Roman numerals to represent the charge of that transition metal. So in order to do that, we have to figure out what the charge is on the ion. So let's look at this one first, TiSO3, or TiS3, I'm sorry. Ti is titanium. Titanium is number 22 on the periodic table. Okay, so it's 22 on the periodic table. It's a transition metal. That tells me that I need to know what Roman numeral to put in the name. So in order to do that, I'm going to look at my anion. the second one, or the last ion written after the transition metal. This is sulfur or sulfide. When sulfur forms an ion, it becomes sulfide. I know that a sulfide ion has a 2- charge, okay? So this 2- charge, I know that because if I go to the periodic table of elements, I should have my charges written here, okay? Sulfur is in group 16 and it forms a 2- charge, okay? So I have a 2- charge, but there's 3 of them. And so when I multiply 2- by 3, the total charge contributed by the sulfur anion or sulfide is a total of 6-. Okay, so that means that whatever charge is supplied by my titanium ion needs to balance that out. So it has to be 6+. But I have 2 of them. So the total charge contributed by both titanium atoms is 6+. In order to figure out the charge on one titanium atom, I have to divide my 6+ by 2. So 6+ divided by 2 gives me 3+. Okay, and I use the charge, I represent the charge as a Roman numeral. So this is titanium 3. And then I just name the anion, which is sulfide. So this is titanium 3 sulfide. This one real quick, if you're watching. This is a error. All right. Let's do these last 2 real quick. So this is nickel. Nickel is number 28 on the periodic table. It's also a transition metal. That tells me that I need to represent the charge with a Roman numeral. Okay, in order to do that, I need to know what charge it's contributing to the molecule. Okay, and so I'm going to start by figuring out what charge the anion is contributing. If Ni is my cation, that means the rest of this whole thing has to be my anion. Okay. PO4, if I look at my polyatomic ion sheet, look it up. PO4 is phosphate. Phosphate has a 3- charge. Okay. There's only one phosphate ion, so it's a 3- charge. There's only one nickel ion. There's no subscript, so I know there's just one of them. And so that has to have a 3+ charge. So this is nickel 3 phosphate. Okay, name the cation, nickel 3, name the anion, phosphate. Done. All right, and last but not least, we'll do this one. Fe is iron. Iron is number 26 on the periodic table. It is also a transition metal. So in order to figure out the charge on this transition metal, I need to first figure out what charge is being contributed by the anion. My anion is all of this inside of here, NO3 inside of the parentheses. Okay, if I look it up on the polyatomic ion sheet again, I find that NO3 has a 1- charge. But this 3 here, this subscript applies to everything that is in parentheses. Okay, so that means I have 3 of these 1- charges. So the total charge contributed by my nitrate ions is 3-. Okay, and I don't have a subscript written in the subscript position here. So that tells me there's only one iron atom. And so that one iron atom has to balance out this 3- charge, so it must have a 3+ charge. So this is my cation is iron 3. My anion is nitrate. So this is iron 3 nitrate. All right, let's go over the crisscross rule. Writing the chemical formulas for ionic compounds, only ionic compounds, utilizes the crisscross rule. So if we look at this, if we look at lithium nitrate, lithium is Li1+. You should have all the charges written on the groups on your periodic table. So lithium 1+, nitrate, remember that ATE ending tells me to go to the polyatomic ion sheet. This IDE ending tells me that it's a monatomic ion, or it comes from the periodic table. Okay. So lithium nitrate is a polyatomic ion. It's NO3-. The crisscross rule says that the charge, or the number on the charge of one ion, becomes the subscript for another one, and vice versa. Chemists don't really write the number 1 very often, and so when we write the chemical formula, we don't need to write 1 as a subscript. This is LiNO3. All right. I'll do this one and this one. All right, chromium, chromium is a transition metal. It's number 24. It is Cr. The 2 in parentheses tells me the charge on my whoops, I stuck on polyatomic ions. All right, so the 2 in Roman numerals here tells me the charge on my transition metal, chromium, and it is a 2+. Okay. Hydroxide is one of the 2 exceptions of the IDE ending rule. Hydroxide is actually a polyatomic ion. Okay, it is OH-. Okay, now the crisscross rule says that this 2 becomes the subscript on OH. This 1 that was here invisibly becomes the subscript on chromium. So when I crisscross those down, I write Cr. I don't have to write the 1. And then OH, I have 2 of them. This 2 applies to all of this. And so in order to make it apply to all of this, I have to use parentheses. And I put the 2 outside of those parentheses. All right, and lead 2 sulfate. So lead is a transition metal. Its PB is it's actually a post-transition metal. It's number 82 on the periodic table. It's PB. And its charge is 2+. And then sulfate, ATE ending tells you to look at your polyatomic ion sheet. Sulfate is SO4 2-. Okay. Crisscross rule tells me that this 2 becomes the subscript here, and this 2 becomes the subscript here. So when I write it, I have PB. This 2 becomes the subscript for PB, so I'm going to write subscript 2. And then I have SO4. This 2 becomes the subscript for that. Remember, I have to use parentheses if I have more than 1 polyatomic ion. SO4, subscript 2. Now, a chemical formula is the simplest ratio of ions. A 2-to-2 ratio is not as simple as saying a 1-to-1 ratio. So you can't forget to reduce. So I can reduce these. When I reduce them, if there's only 1 polyatomic ion, I don't need parentheses anymore. So I erase those, and my new chemical formula is just PbSO4. Okay. All right. Describing a covalent bond. A covalent bond is the sharing of valence electrons. Okay. Here it's asking to describe the differences among single, double, or triple bonds. Single bond shares 2 valence electrons. Double bond shares 4 valence. And a triple bond shares 6 valence. okay? Specific compounds to demonstrate this. You guys have seen the fluorine, F2, okay? A double bond, carbon dioxide has double bonds, and a triple bond, carbon monoxide has a triple bond in it. Four properties of covalent compounds. All right, covalent compounds. They don't conduct electricity. You should be able to use these notes. Let me see. Uh-oh. You should be able to use these notes here to help you out. Okay, but they don't conduct electricity. They have low melting point and boiling points. I'm going to put BP and MP for short. They don't separate in water. They don't separate in water, and they can be solid, liquid, or gas at room temperature. Whereas ionic compounds are typically solid at room temperature. Okay. All right, naming covalent compounds. These ones you just have to use prefixes. I'm not going to do these ones with you. Just go ahead and use you can use the key if you need, if you want to check your work. Don't worry about these two. I taught common names for molecular compounds last year and I didn't this year, so I apologize I didn't take those out. All right, drawing Lewis structures. This is probably some of the most beneficial part of this video for you. All right, so we're going to draw Lewis structures for the following. Remember, your handout for drawing Lewis structures. You can't use it on the exam, but it'll help you practice, and then you can formulate or summarize it on your little note card. So the first thing you want to do is determine the central atom. This is the most electronegative, or the one that's furthest left on the periodic table. So when we're looking at carbon dioxide, we have carbon and oxygen. When we look at the periodic table, we see that carbon is further left. Okay, so carbon is going to be our central atom. So we put carbon in the middle. And then the next step is to put the other atoms around your central atom. So I have two oxygen atoms. I'm going to put around it like that. The next step is to calculate the number of valence electrons. Okay, so if we have CO2, we're going to calculate the number of valence electrons. This should be written on your periodic tables. Carbon has 4 valence electrons, oxygen has 6, and there's 2 of them here. 4 plus 12 is 16 total electrons. I'm going to add single bonds first. I'm going to add bonding pairs connecting the atoms. Each bond or each line represents 2 electrons. So I need to subtract 2 electrons per line from my total. So I subtract 4 electrons and I end up with 12 total electrons that I can distribute as lone pairs. All right. So when I distribute these as lone pairs, I have to start with the outside atoms. I add 2 at a time in order to make an octet. Okay. I have 12. So I'm going to add 2, 4, 6. When I add those 6, I give this oxygen an octet, or 8 valence electrons. It had 2 with this bonding pair. 4, 6, 8. So I added 6. I have 6 left. I can move on to my next outside atom. 2, 4, 6. When I add that 6, I have a total of 8. Okay, and now I don't have any more electrons to add. But I have a problem because this central atom doesn't have an octet. Everything needs 8 valence electrons. That's the whole shebang. That's what drives all of this, is atoms want to be stable. Okay. Now, if I don't have any more lone pairs to give, what's going to happen? Carbon is going to steal a lone pair and make a double bond here. Okay. And then I can check 2, 4, 6. I still don't have an octet. So carbon's going to steal another lone pair from this oxygen atom and form another double bond. So carbon dioxide looks like this. Okay. All right, chloroform. I have CHCl3. First step, determine your central atom. My central atom is carbon. It's the furthest left on the periodic table except for hydrogen, but hydrogen can never be the central atom. Okay, hydrogen, instead of following the octet rule, follows the duet rule. So it needs 2 valence electrons to be happy. On the periodic table, we see that hydrogen only has 1 valence electron, but to get a full valence shell, it wants 2. So hydrogen can't be in the middle. Other than that, carbon's the furthest left, so carbon goes in the middle. Everything else goes around it. We have 3 chlorine atoms and 1 hydrogen atom. So those all go around it. Connect, or I'm sorry, add up the total valence electrons. Carbon has 4 valence electrons, hydrogen has 1, and chlorine has 7, but there's 3 of them, so we have to multiply it by 3. We end up with 4 plus 1 plus 21. That gives us a total of 26 valence electrons to add. First, I add electrons as bonding pairs to connect all of the atoms. It's 2 electrons per bonding pair, so I've added 2, 4, 6, 8. 26 minus 8 is 18. So I have 18 left to distribute around the outer atoms. My central atom already has an octet. Okay, it's very rare that the central atom breaks the octet rule. So I'm going to add 2 at a time, giving all of my outer atoms an octet except for hydrogen. Hydrogen doesn't get lone pairs, it's happy with 1 bond. 2, 4, 6, 8, 10, 12, 14, 16, 18. All right, so I added all of them. Everything has an octet. Hydrogen has a duet, so we're good. Hydrogen cyanide is next. All right, first things first, determine your central atom. It's going to be carbon. Carbon goes in the middle. Everything else goes around it. Calculate the number of valence electrons you have. Hydrogen has 1 valence electron. Carbon has 4, and nitrogen has 5. Add those up, and you have a total of 10 valence electrons to distribute around your molecule. I add 2 4 valence electrons as bonding pairs. 10 minus 4 is 6, so I have 6 left to distribute. I don't add any lone pairs to hydrogen, so I'm going to add lone pairs to nitrogen until it has an octet. 2, 4, 6. I used all of them to give nitrogen an octet. I don't have any more left. Nitrogen has an octet. Hydrogen has a duet and is happy. Carbon, though, doesn't have an octet yet, and it needs one. So it's going to steal a lone pair from nitrogen and form a double bond. When I check to see if carbon has an octet yet, I see it only has 2, 4, 6 around it. So it's going to steal another lone pair from nitrogen and form a triple bond. And then I check to see hydrogen or carbon has 2, 4, 6, 8 valence electrons. Nitrogen has 2, 4, 6, 8 valence electrons, so it's happy. All right, beryllium chloride. Determine your central atom. Beryllium is in group 2. It's further left than chlorine, so it goes in the center. The other atoms, chlorines, go around it, 2 of them. Calculate the valence electrons. Beryllium has 2, chlorine has 7, but there's 2 of them. 2 plus 14 is 16 valence electrons total. I add single bonds to connect everything, 2 electrons per bond. So that's 2, 4, 16 minus 4 is 12. I have 12 electrons left. I'm going to add them to my outer atoms first. 2, 4, 6, that gives this chlorine an octet. I have 6 left. 2, 4, 6, that gives this chlorine an octet. I don't have any left. My beryllium still doesn't have an octet. So I need to steal from chlorine at a double bond. 2, 4, 6, beryllium still doesn't have an octet. So I'm going to steal from this chlorine and add a double bond. Now everything has an octet and is happy, so we're done. Nitrogen fluoride. NF3. Determine your central atom. Nitrogen is further left, so it's going to be in the center. Surround your central atom with the other atoms. I have 3 fluorines. Next step, add up your valence electrons. Nitrogen has 5 valence electrons, fluorine has 7, and there are 3 of them. 5 plus 21 is 26. 26 valence electrons. I need to add 2, 4, 6 of them as bonding pairs. That leaves me with 20 left to distribute to give everything an octet. I'm going to start with my outside atoms first, giving each one an octet one at a time. 2, 4, 6, 8, 10, 12, 14, 16, 18. I used up 18 of those lone pairs, so I have 2 left. Now I can move on to my central atom to give it an octet. Everything has an octet and is happy. I use all my electrons. I'm done. Boron trihydride. All right. Boron goes in the middle. Hydrogen can't go in the middle, so it's the only one that goes in the middle. Surround your central atom with the rest of your atoms. Add up the number of valence electrons that you can have. Boron has 3 valence electrons. Hydrogen has 1. Whoops, but there's 3 of them. 3 plus 3 is 6, so I have 6 valence electrons that I can add. I need to add 2, 4, 6 of them as bonding pairs, and so I'm done. Nitrate. All right, determine your central atom. Nitrogen is going to be your central atom. It goes in the middle. Everything else goes around it. 3 O's. Calculate your valence electrons. Nitrogen has 5 valence electrons. Oxygen has 6. There's 3 of them there. Very important to remember that if there's an electrical charge, you need to add or subtract valence electrons. Because it is negatively charged, that means there's an extra electron there, so I need to add 1 electron. 5 plus 18 plus 1 is 24 total electrons that I can distribute to my compound. I need to add 2, 4, 6 of them as bonding pairs. 24 minus 6 is 18, so I have 18 left to distribute to give everything an octet. 2, 4, 6, 8, 10, 12, 14, 16, 18. I've used all 18 of them, but I still don't have an octet on my nitrogen here. So nitrogen is going to steal a lone pair from an oxygen and form a double bond here. Now remember, with electrically charged ions, I put brackets around them and put the charge on the outside of the brackets. All right. What do the letters in VSEPR stand for, and what is it used for? Or what does the theory say and what is it used for? VSEPR stands for the valence shell electron pair repulsion. Okay, that's what the letters stand for. Valence shell electron pair repulsion. The VSEPR theory says that electrons, electron pairs in the valence shell around a central atom repel each other. Okay? They will repel each other and spread out as far away from each other as they can, as possible, and spread out as far away as possible. This is used to determine molecule shapes. Molecule shapes, also known as molecular geometries. Okay. So the valence shell electron pair repulsion theory, which is a mouthful, but it's really not that complicated. It just says that the electrons in the valence shell around a central atom come in pairs, bonding pairs and lone pairs. And when they're around a central atom, because electrons have the same charge, they repel one another. And when they repel one another, you have electrons on one side repelling, electrons on another side repelling. And so this repulsion causes them to spread out around a central atom as far as they can. And this causes all electron pairs around a central atom to equally distance themselves from one another. Okay. All right. Draw the Lewis structures and determine the molecular geometries for the following. All right. So sulfur trioxide, SO3. We're going to determine the Lewis structure. All right. I'm going to count up the valence electrons first, and then I'm just going to draw them real quick. Okay, so I'm going to do these a little bit faster than I did in the previous section. If you need help drawing Lewis structures, please go watch number 16, and I'll go step by step on those. All right, sulfur trioxide. We have SO3. Sulfur has 6 valence electrons. Oxygen has 6, but there's 3 of them. 6 times 4 is 24, so you have 24 valence electrons. Sulfur is your central atom here, and we've got 3 oxygens bonded to the sulfur. So by bonding, I've used 2, 4, 6 valence electrons. That gives me 18. 2, 4, 6, 8, 10, 12, 14, 16, 18. I've used them all up. I don't have an octet on my central atom, so I do this double bond. Okay, so that's sulfur trioxide. Now, in order to determine the molecular geometries, you need to use your VSEPR resource. That's this one. Okay, that's this table that we made. All right, now we're looking for something. Okay, when we use this resource, we're only looking at the pairs of electrons around a central atom. Sulfur is our central atom here. We determined that in the beginning. We need to remember that a double bond only counts as one bonding pair. Okay, so in our image here, we have SO3. It has 1, 2, 3 bonding pairs and 0 lone pairs. So we go to our table here. We look for something with a total number of 3 electron pairs coming off the central atom. 3 of them are bonding, 0 are lone. So this is a trigonal planar. Okay, so this is a trigonal planar. All right. Silane or SiH4, that's the common name for this compound. Si is going to be the central atom. So we put Si in the middle. Oops. Si. We're going to have 4 H's bonded to it. Okay, if we count up the total number of valence electrons here, silicone has 4, and we have 4 hydrogens, each with 1. So we have a total of 8 valence electrons. I used all 8 of them, 2, 4, 6, 8, so I'm done. Now, I'm going to go look for something. My central atom, silicone, here has 1, 2, 3, 4 bonding pairs and no lone pairs around it. So in my resources, I'm going to find something with 4 bonding pairs and 0 lone pairs. This is a tetrahedral. Okay. So this is a tetrahedral. Tetrahedral. Just like it sounds. Okay. Last but not least, sulfur dichloride. So SCl2. If I calculate, sulfur has 6 valence electrons, chlorine has 7, there's 2 of them. I have a total of 20 valence electrons that I can put here. Sulfur goes in the middle, chlorine here, chlorine there. I've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So I used all 20 of them. Everything has an octet. We're good. So now around my central atom sulfur here, I have 2 bonding pairs and 2 lone pairs. So I need to go to my table here and find something that has a total number of 4 things coming off the central atom, and 2 of them are bonding pairs, 2 of them are lone pairs. This is a bent. Okay, this is a bent. And sometimes people specify bents by the angle because there's 2 different bents. All right. Number 19. I'm getting parched talking so much. All right, number 19. Describe the shape and give the bond angles for a molecule of nitrogen tribromide, NBr3. To know the shape, we got to draw the Lewis structure. We got to know how many bonding pairs and how many lone pairs are coming off the central atom. So even though in the instructions it doesn't say, we still need to do it. Nitrogen has 5 valence electrons. Bromine has 7, but there's 3 of them. 5 plus 21 is 26. Nitrogen is going to go in the middle. I use 2, 4, 6 electrons to make the bond, so I have 20 left. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. Okay, everything got an octet, so I don't need to add any double bonds or anything like that. I'm good. So now I'm going to go to my resources and I'm going to find something that has 1, 2, 3 bonding pairs and 1 lone pair. And when I go and I look at that, I see something with 3 bonding pairs and 1 lone pair is a trigonal pyramidal. Okay, so I'm going to go in and name it. This is a trigonal pyramidal. So it has a trigonal pyramidal shape with 109.5 degree bond angle. Okay. All right, silane or silane. Oh, I already did this one up here. This is silly, right here. We've already done this one. So if you did it twice, I'm sorry, but I'm not going to do it twice. Okay. All right, this one's important. There are 2 different types of bent molecular shapes. Describe the differences between them. Well, if I go to my resources here, my table, there are 2 different kinds of bents. I have this one and this one. Okay, I see a bent right here and a bent right here. So, what are the differences between them? Well, one of them has 4 things coming off the central atom, and the other one only has 3 things coming off the central atom. So, because of this, the bond angle is affected. All right, oops. All right, so we can use that and say, what are the differences between them? Well, one bent molecule has 3 pairs of electrons coming off the central atom. 2 of them are bonding pairs. 1 is a lone pair. This molecule has a bond angle of 120 degrees. Okay, see that? It has a bond angle of 120 degrees. The other one here, this is the other bent. It has 4 things coming off of the central atom. 2 are bonding pairs and 2 are lone pairs. This extra set of lone pairs, or the extra set of things, the extra set of electrons coming off the central atom, if I have my lone pairs here, it actually pushes those bonding pairs closer together. And so it causes the bond angle to decrease. They're closer together, so the angle is smaller. Okay, so if we wanted to go and describe that, we would just say the other molecule. Okay. The other bent molecule has 4 electron pairs on the central atom. Two of them are bonding. 2 are lone pairs. 2 are bonding pairs, 2 are lone pairs. The bond angle is 109.5 degrees. This is important because the second one has more electron pairs around the central atom, they cannot repel as far from each other. Valence shell electron pair repulsion theory explains this. Okay. All right, that's it.